This is the second lecture from Chapter 10, all about thermochemistry, and the focus of this lecture will be enthalpy. And just a quick reminder, we have talked about for our purposes for reactions conducted under constant pressure, and which is everything that's done under normal atmospheric pressure, that Q, heat, equals change in enthalpy. Okay, so just keep that in mind as we go through these pages. During the last PowerPoint, I talked about the Q-MCAT equation. Okay, so just put it up here to remind you. And we mainly focused on using that as well as our other equation for phase changes, which was Q equals whatever the quantity is times enthalpy of either vaporization or fusion. And we used that mainly when we were talking about heating curves, and we were calculating the heat involved in raising the temperature of a substance. There's one more thing I want to go over that uses the MCAT equation that can be a little bit tricky, so I just want to work one out for you. There are some cases where there'll be a problem where typically a chunk of metal will be heated up to a certain temperature and then dropped in a container of water. And of course, the metal is going to release its heat to its surroundings, which is the water, and heat's going to continue to flow from the hot metal to the cooler water until they are both at the same final temperature. And so that type of setup, sometimes you're asked if it's an unknown metal, you're asked to find the specific heat capacity of the metal. Other times you may be able to ask for something else like mass or whatever. But here's an example for you. In this case, we have a mass of metal, 25 grams, and it was heated up to 100 degrees Celsius. Then it was put in a calorimeter containing water. The initial temperature of the water, 19.3 degrees Celsius. The system and surroundings were allowed to reach thermal equilibrium, which means, and remember, this is really important for these problems, y'all, that TF of the surroundings equals TF, final temp of the system, once thermal equilibrium is reached. So when you have mixed two things together and they don't mix to make a solution, okay, like metal and water, then you have to set it up like this. What this equation simply says is that the heat released by the metal is equal to the heat absorbed by the water, and the negative sign here is really important, okay, because it's showing that one is releasing heat, one is taking in heat. And this is probably the most common mistake that students make when working this type of problem, is they forget to put that negative there. And so then basically what you're doing, multiplying the mass of the metal times the specific heat of the metal times delta T that the metal underwent. Now, just kind of a reminder here, change in temperature, equals final minus initial. That's also important to remember that order, final minus initial, okay? And then again, mass of the water, specific heat capacity of the water, and change in temperature that the water experienced. So here's a problem like that worked out. I did change the parameters a bit because I copied and pasted one that was already available instead of making one up. But you basically remember that you need all the information in MCAT for both the water, which constitute the surroundings, and the metal. So plugging in the information we know, mass of the metal, that's water. Mass of the water, this is specific heat capacity of water. Specific heat capacities, unless you're solving for one, you have to be given that information. There are tables of known specific heat values. And the temperature change that water underwent, so remember, change in temperature is final minus initial. Okay, so the equilibrium or the final temperature is 27.8, and the initial temperature for water it's 23.7. So that's where the 4.1 degrees comes from. And again, remember the negative sign, and doesn't matter what side it's on. It's just showing that the absolute value is the same, but the heat's going in different directions. Here's the mass of the metal. You're solving for a specific heat capacity of the metal, and this is the temperature change that the metal is undergoing. And I just realized it's not showing very much, but there is a negative in front of the temperature change, because looking at calculating temperature change the metal undergoes, the final temperature for both is 27.8. The initial temperature for the metal is 100. Okay, and so the delta T for the metal is minus 72.2, and now both of the minuses on this side will cancel out, right? Specific heat capacity is always a positive value. Okay, so that's a type of problem. There are practice worksheets posted in D2L so you can get a little more practice. Oops. Onward to talking about enthalpy. Enthalpy is huge in thermochemistry. It's probably the most important topic we're going to go over. So there is a way to actually measure enthalpy, keeping in mind that under constant pressure it's equal to Q. So there are ways to calculate that, of course, with calorimetry, the QMCAT equation. But there are also ways to calculate it. If you can't measure it directly, there are ways to estimate it by calculation, which we'll go over. So change in enthalpy, as change in anything, is typically final minus initial. If we're talking about a chemical reaction, the change in enthalpy for the chemical reaction would be total enthalpy of products minus total enthalpy of reactants. So it's kind of like final minus initial, right? So enthalpy, and this will be a multiple choice type question, so make note, make sure you know it. Enthalpy, change in enthalpy is called a state function. Okay, a state function is something that does not depend on the path taken. So the easiest example I like to present is look at the image in the bottom. Okay, so you have a mountain, and there are different ways you can get from the base of the mountain to the top, right? You can go straight up, or you can weave back and forth. Okay, so a state function when using this image might be altitude. Well, it is altitude, right? Because change in altitude, because the change in altitude is simply the difference in altitude between the top and the base. And so change in altitude would be a state function, right? Because it doesn't depend on the path you take. What if it's not a state function? What if it does depend on the path? That's called a path function. Okay, we won't talk much about those. But a path function is something that does depend on the path you take, just like it says. So the energy exerted to get from the base to the top would be a path function, because you're going to exert a lot more energy weaving back and forth to get to the top than you would if you went straight up. Now, because enthalpy is a state function, the enthalpy change in the forward direction of any reaction is equal in magnitude but opposite in sign to the change in enthalpy going in the reverse direction. Okay, so combustion, in this case that's natural gas, methane. Combustion reactions are always exothermic, and if you remember the sign convention, that means that enthalpy will have a negative sign. So combustion reaction going in the forward direction is negative 890 kilojoules, which means if we could reverse this combustion reaction, it would absorb 890 kilojoules. Another quick definition for you is enthalpy, in addition to being a state function, is what we call an extensive property. Any extensive property is a property that depends on how much of the substance you have. Okay, so what that's telling us, let's say you looked at a reaction like this. This happens to be the combustion of propane. You're going to see a lot of combustion reactions in thermal chemistry, right? When we combust propane, when we combust exactly this amount, shown by this equation, which is 1 mole of propane, we will get 2,044 kilojoules of energy released. So what if you were asked in a question, which you will, how much energy, or what's the enthalpy change if we combust 2 moles of propane, or if we combust 5 moles of propane? So you need to learn to use the change in enthalpy given with a balanced chemical reaction as a conversion factor. In this case, because there's only 1 mole of propane, it would be fine to say the delta H is minus 2044 per mole, right? And then we can think of it more as a conversion factor. So if I said, okay, what is the delta H for 2 moles of C3H8? You could set up your dimensional analysis equation to say, okay, I know there are 2044 kilojoules per 1 mole of C3H8, right? So that means there would be 4,088 kilojoules released if 2 moles were combusted. So let's talk about actually measuring enthalpy changes for reactions first. So anytime you measure something to do with thermochemistry, it's with a calorimeter, and that's basically what we've shown so far, insulated containers that don't let heat get in or out. So here is an example of using the calorimeter to calculate delta H of reaction. Pay real close attention to the difference between this QMCAT type of problem and the one we did for determining the specific heat capacity of a metal. Remember when we had a metal, we said that Q of the metal equals minus Q of the water, right? Water is the surroundings, the metal's the system. We can't do this in this reaction, and I'll explain why. So let's read the problem first. You have a certain volume of hydrochloric acid solution mixed with a particular volume of sodium hydroxide solution. And those two are going to react, right? An acid plus a base gives a salt and water, right? Hopefully you remember that from 1211. And it is, well, I won't tell you. It's going to be an exothermic reaction, so we expect delta H to be negative. You can also tell it's exothermic because what happens to the temperature of the water. So it's good to just kind of read the question and scope out what you can find out before you do the calculation. The fact that the water is heating up means the system, in other words, the reactants, are producing heat and releasing it to the surroundings, which is the water. All right, so let's go ahead and work through this. The one hint I want to give you is when you add two things together in a calorimeter and they mix to make a solution, okay, you only use one QMCAT equation. There's one QMCAT equation for the whole solution. You don't set up two of them like you do with the metal and water. Metal and water do not mix together to make a solution, so they each need their own QMCAT equation. All right, so let's look at solving this. Again, let me write the QMCAT equation. So now, instead of looking at the mass of the individual components, in other words, you don't just get the mass of the sodium hydroxide solution or the mass of the HCl solution. You have to do the total mass of the final solution, okay? So let's figure that out. We don't have mass, right? We have volume and molarity. So this is going to be some review for you from 1211. So if you need to go back, remember I have a YouTube channel, you have your textbook if you need to go back and look at molarity and how to do calculations with it. So molarity is moles of solute divided by liters of solution. If you like the triangular help things to help you rearrange that equation, that looks like this. Now, this calculation may be a bit tricky for you, and I deliberately put this problem, it is a little tricky, in as an example I'm going to work through because you will encounter it in your homework, okay? And I want you to have an example. So we are not given the total combined grams of those, okay? So the easiest way to do it is to use the density, right? So the density of each, that means there's 1 gram per 1 milliliter of the solution, and that means that if we find the milliliters, the total milliliters of solution, that will be equal to the grams. So let's find the total milliliters. There are 0.2 liters of each of the solutions, so we have a total of 0.4 liters. Of course, there are 1,000 milliliters per liter of solution, so that means we have 400 milliliters. Using our density as a conversion factor, if we have 400 milliliters and the density is 1 gram per milliliter, that means we have 400 grams. All right, so now we know the mass of our entire solution, and we can plug that into our QMCAT equation. So mass is 400 grams. Again, you will always be given the specific heat capacity of water, or whatever you're working with, 4.18. And what is the delta T for this reaction? So remember, it's final minus initial. The final temperature is 23.48. The initial is 22.15. So if you multiply all those together, you get that the heat produced from this is 2220 joules. Now, what I'm getting ready to say right now may be a bit confusing, so if you're spacing out on me, tune in for a minute, okay? So, the quantity of heat that is released by this reaction is 2,220 joules, okay? And again, that's for the quantity that was in the calorimeter, okay, which is 0.04 moles of each of them, actually. So if you look back at the reaction and the question wants to know enthalpy of reaction for the reaction as written here. As written here, there are 1 mole of both the sodium hydroxide solution and of the HCl solution. Okay, there's only 1 of each. So this value that you have to provide, they didn't say what is the delta H for the quantity given in the question. They said what is the delta H for this reaction as written. Okay, so that means you need joules per mole. Okay, and what you have now is 2220 joules per 0.0400 moles of each, okay? So simply simplify that, divide one by the other, and you get 55,500 joules per mole, and that is the answer. Now, one more important thing is this is the delta H. This is what the water or surroundings experiences. This is really, really important, y'all. The really common struggle students have in thermochemistry is sign, plus and minus sign. So this is really important. Any calorimetry study you do, the temperature changes are the temperature changes that the surroundings are undergoing. So if the question asks you, what is delta H for the system or the reaction is your system, it's minus whatever you got for the surroundings. So the actual answer here is minus 55,500 joules per mole. This is an exothermic reaction. So what we've talked about so far are standard calorimeters, and if you do a calorimetry experiment in the lab, it's going to be 2 styrofoam coffee cups tucked inside of each other, and that's our way of insulating. And in an actual lab, it's usually a metal container that has like a vacuum insulation interior layer. But there are a lot of reactions that cannot accommodate big changes in pressure or extreme heats, and so there's something called a bomb calorimeter. That's not as important as understanding how to do calculations with a regular, but it's something that will probably show up as one question on your test. So bomb calorimeters, the bottom line is they're designed specifically for combustion reactions. And so the calculations done with them are just a pinch different. So let's look at a sample problem using a bomb calorimeter. You can pretty much assume that any calorimetry problem involving combustion is going to be a bomb calorimeter. Notice also the equation for the bomb calorimeter is different than what we're used to. Okay, so what we're used to, the QMCAT equation, you need the mass of the substance, you need the specific heat capacity of the substance. And here, in a bomb calorimeter, you use what we refer to as specific heat capacity of the calorimeter itself. And finding that requires an experiment itself. So this is an example that benzoic acid, or something that's known real well, is real commonly used to find the specific heat capacity of a bomb calorimeter. So here's an example of calculating that. They're asking you for a specific heat capacity of a particular calorimeter, and it's saying if you burn exactly 1 gram of benzoic acid, the temperature increases by 7.248 degrees Celsius, and that this much energy is released. So simply rearranging this formula to solve for specific heat capacity of the calorimeter. So now you take Q, the heat released, which they gave you, 26.38, divided by the change in temperature. This is specific heat capacity of the calorimeter. Now, just as often, you will be given specific heat capacity of a certain bomb calorimeter. It varies depending on the setup of the calorimeter. And you will be asked to find, let's say, Q or delta H. So let's just go in the reverse directions. Let's assume that we knew this C value, and you were asked to find the delta H of reaction for combustion of benzoic acid. So remember, again, we're assuming delta H for our purposes, constant pressure, equals Q, that it's one and the same. And so let me take a minute and erase. Now, what if you were asked what delta H for this reaction is? How would you get from Q, which they gave you, to delta H? Now remember, delta H typically has units of per mole, right? Because it's a combustion reaction now. So if we were to write out a reaction, which you don't really need to do, but benzoic acid, any combustion reaction has oxygen as a reactant. The products of combustion are always the same. Okay. So what if the problem asked you, what is the delta H for this reaction is written for combusting 1 mole of benzoic acid? How would you do that? The only thing you need to do then is to figure out the moles of benzoic acid. Okay, we know that 1 gram of benzoic acid releases 26.38 kilojoules. So let's figure out how many moles are in 1 gram, right? So 1 gram benzoic acid, and I'm going to cheat and look up the molar mass. And it is 122.12 grams per mole. And by the way, if you didn't have me for 1211, you make sure when you are using molar masses in calculations that you have at least 2 digits to the right of the decimal. Let me pull out my handy dandy calculator here. Okay, so we have 0.00819. I'm going to round more than I should because I'm out of room. Moles of benzoic acid. So now, to get the delta H for that reaction as written, it is simply 26.38 kilojoules divided by 0.00819 moles, and that will give you delta H of reaction, okay, per mole. Assuming I plug that into my calculator right, I get the delta H is 3,221 kilojoules per mole. All right, so I mentioned before that enthalpy of reaction can be measured with a calorimeter, and those are the problems we've done so far. But in some cases, it's impractical or even impossible to measure the enthalpy of a reaction. So in that case, there are various ways that we can estimate enthalpy of reaction by doing a calculation. So the rest of this PowerPoint is going to be going over the 3 ways to calculate enthalpy of reaction. The first is using a process called Hess's law. The second is using what we call enthalpies of formation for reactants and products. And the third is to use the bond energies to calculate. So as you might have already noticed, there are a ton of calculations in this unit. So my very, very strong recommendation to you is that right away you print out or at least pull up the practice worksheets I've posted in D2L on week 1 and week 2 and begin working as many problems as possible. It is not for credit, but the more you can work, the more ready you're going to be for the first exam. The first method for calculating enthalpy of reaction we're going to learn about is using Hess's law. Hess's law simply says that if by adding 2 smaller reactions or different reactions together, you get a third reaction, which is the reaction you're interested in, you can also add together the enthalpies for those different reactions to get the enthalpy of the reaction you're interested in. That's a lot of words, so let me show you with this diagram. Let's say that you were interested in this particular reaction, okay? So just writing it out in what you're used to. Methane combined with 2 moles of water gives 4 moles of hydrogen gas and carbon dioxide. Okay, but let's say that you were not able to, for whatever reason, measure the delta H of reaction for this. But you could find other reactions that when added together gave you this reaction. So let me show you, for example, if you look at this first reaction, which would be methane and water, so the reactants start out the same, right? And the products for this first reaction, carbon monoxide and 3 moles of hydrogen gas. Okay, so, and we know the enthalpy of reaction, that's known. Let's say it's in a textbook, a reference book, whatever. And then in a second reaction, which would be here, so that's carbon monoxide plus, in other words, the products from the first reaction, plus water, give 4H2 and CO2. All right. Now, if we were to add these 2 reactions, reaction 1 and reaction 2, if we were literally to add them like a math equation and cancel out the things that show up on both sides of the arrow, guess what? We would end up with our reaction of interest, and I'll show you that, the mechanics of that in a bit. So what Hess's law says, okay, if the reactions add up to give you the reaction you're interested in, you can also add together the known enthalpies of reactions for those and get the enthalpy of reaction for the reaction you're interested in. So let's work through an example. There are 2 rules that you have to follow and remember when using Hess's law. When you are given, because typically a Hess's law problem will say, using the following reactions, figure out what the delta H is for this third reaction. So sometimes you have to reverse a given reaction to make it add together correctly. So if you do have to reverse a reaction, in other words, you make what was the product become the reactant and vice versa, then change the sign for the delta H value for that reaction. If you have to end up multiplying it by a coefficient so that it adds to give you what you want, so looking at this reaction, let's say we multiplied all the coefficients by 3, then you also need to multiply the enthalpy of reaction by 3. Okay, so remember those two rules, make a note, and here's an example. You are given 3 sample reactions and asked, using these 3 actions, calculate the heat of reaction for this guy. So you have to figure out how to combine these 3 reactions and then do the same thing to their delta H values. Now remember, when working a Hess's law problem, you can only change the given reactions in 2 ways. You can reverse them if needed, like if you see that the reactants you need are on the product side, you can reverse. Or you can multiply the coefficients of a given reaction by any factor that you want to, as long as you remember to multiply the delta H value by the same factor. So let's look at each of the 3 given reactions, see if we can figure out. Always keep in mind the reaction you're trying to get to. Now I'm going to look at each of these 3 given one at a time. The first thing I look for is that the reactants and products are on the correct side. Okay, so I see right away that I want C2H2 as a product. In this first given reaction, it's on the reactant side. So I know that I need to flip. I'm just going to say reverse that reaction. Okay, and so if I actually wrote it out reversed, you would get down here. Okay, and when you do reverse it, how funny, it's rounded up here more than it is here. When you reverse the reaction, remember to reverse the sign of the given delta H value. Okay, now let's, the coefficients. After you decide whether or not it has to be reversed, then look at the coefficients, okay, and there's a 1 in front of both, and so you don't have to multiply by any factor. Go ahead and switch now to given reaction number 2. I see in that carbon is a reactant, and it is on the correct side. And some of the reactants you're going to see don't even show up, like oxygen and CO2 aren't even in, so you can't use those, obviously, to make a decision. So even though carbon is on the right side, there aren't enough of it, okay? We need 2 carbons. So that means what I'll do with this reaction is multiply all of the coefficients by 2, okay, as well as the delta H value by 2. So when I do that, come down here and see, multiply all the coefficients by 2 and the delta H value by 2. All right, look at the third reaction. The only thing that shows up in both is the H2. It is on the correct side. It's on the reactant side as it should be, and it's there in the right with the right coefficient. So I'm not going to do anything to manipulate reaction number 3. I'm going to leave it as it is. So now what you need to do to verify you've done everything right, and also that the reactions react or add together to give you what you want, and also if you're asked to show your work, you literally want to add them together. So you're going to add all of the reactants, for all 3 reactants, all 3 reactions. Okay, and then you're going to put your arrow and you're going to combine all of the products together. Wish I could write smaller. Oopsie. H2O, I can't even fit that in. Anyway, I'm hoping you can see what I've done. So once you write them all out, then you cross out what's the same on both sides. So in this case, let's see, what do we have on both sides? We have water. You can actually do it this way. It's going to be easier, isn't it? There's a water molecule on the reactant side of one and a water molecule on the product side, which means they're going to cancel out. And looking at my long way, you could show it like that, okay? What else shows up on both sides? Okay, we have oxygen gas on the reactant side of two of them and on the product side of the other. So now, just like any math equation, if you want to combine like terms, so we have 2.5 oxygen molecules on the reactant side, and 5/2 is 2.5 oxygen molecules on the product side. So the oxygens all get canceled out too. Okay, is there anything else that we can cancel out? Carbon dioxide. All right, so what are we left with? After you cancel out everything that looks the same on both sides, we are actually left with this, the reaction we want. So you have verified that you can add these three reactions together. And so now all we need to do is add together, keep in mind the correct signs of all the delta H values. When we do that, we get that the delta H for the reaction of interest is 226.7 kilojoules. So obviously that's kind of these are almost kind of fun, believe it or not. If you're not under a lot of pressure, they're kind of like a puzzle. But again, there are practice worksheets posted in D2L that you can start working through. All right, so Hess's law is the first method for calculating enthalpy of reaction. The second is using what we call enthalpy of formation. So there are several different types of enthalpy, and usually they're designated with a subscript. So enthalpy of reaction will typically look like this. Enthalpy of formation is different. The little degree sign is pronounced not. It just means standard condition. Now, enthalpy of formation, I'm first going to give you a definition, and that will be a multiple choice, probably on your first unit test from me, as well as on the standardized finals, so make a note of that. Standard enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its elements, okay? So let's say that we want to know enthalpy of formation for nitrogen monoxide, okay? So you could, nitrogen monoxide is made from nitrogen, the element oxygen, right? And so you might think, okay, well, here it is. It's made from its elements. No, because you need to remember that the definition says 1 mole of the substance of interest. So this is the one time it's okay to use fractional coefficients. In this case, we have to, because to get the enthalpy of formation, we need only 1 mole of the substance, okay? So the enthalpy of formation for nitrogen monoxide is 90.3 kilojoules. So this is just definition, and now we'll talk about using these enthalpy of formation values to get enthalpy of all different types of reactions. There will be enthalpy of formation tables, which you'll be given too. I think I posted one in the practice worksheet area for you to be working through problems. Your textbook has one, I'm sure, in an appendix also. All right, so the formula to calculate enthalpy of reaction from enthalpy of formation is the sum of enthalpy of formation of all the products, and this N just means you have to take into account the coefficients in the balanced reaction. So if there are 2 of a certain product, you need to multiply the delta H of formation by 2. So anyway, the sum of all the enthalpy of formation of the products minus the sum of all the enthalpy of formation of the reactants. So here's an example. This one's much easier, really, than the Hess's law. This is just, you have to look, probably proofread to make sure you don't make silly errors. So in this case, remember it's products minus reactants. So we want enthalpy of formation of carbon dioxide, multiply it by 3. Enthalpy of formation for liquid water, since there are 4 of them, multiply by 4. Make sure you put brackets around all of your products. Again, messing up signs is a big problem. Then you're going to subtract from that the sum of enthalpy of formation of all the reactants. So we have 1 propane and 5 oxygen. All right, then you would go to your table of heat of formation or enthalpy of formation values and you would plug in. I want to make a really big deal of something now. Look at what's 0. What is 0? The enthalpy of formation of oxygen is 0. This is critical, another really common mistake, okay? Enthalpy of formation for any element in its standard state, that means how it exists in nature, is 0, okay? Heat of formation, enthalpy of formation for any element in its standard state is 0, okay? Oxygen in its standard state is a gas that's diatomic, okay? So anyway, then hopefully you've got all your brackets and signs correctly. So the enthalpy of reaction for the combustion of propane is minus 2,219.9. Now, just remember, combustion reactions are always exothermic. Their enthalpy will always be negative. That'll kind of help you. So if you don't get a negative value, you probably have a math error. All right, the third way of calculating enthalpy of reaction is using bond energies. So in this case, you're going to need to be able to draw Lewis structures so that you can determine if bonds are single, double, or triple, because that's going to affect your values. So in this case, the example, combustion of methane. Methane has all single bonds, right? And oxygen. If you need a reminder on how to draw Lewis structures, again, you can either go to my YouTube channel, Lori Maffei, or your textbook, or just Google, but you need to be real good with that. So the Lewis dot structure for molecular oxygen looks like this. Those are supposed to be dots. My stylus is not really very good. Okay. But there are double bonds in molecular oxygen. Carbon dioxide, the product, also has double bonds. And then water is single bonds. So basically what you're going to be doing is you are going to be calculating the energy required to break all of the bonds in the reactants. So what bonds are you breaking here? 4 carbon-hydrogen bonds, and there'll be a table of bonds, right? And you're also breaking an oxygen-oxygen double bond, okay? Now, pay attention to coefficients because you are actually breaking 2 oxygen-oxygen double bonds. Now, it always requires energy to break a bond, okay? So breaking bonds is always endothermic, will always require input of energy, just like breaking anything. Now, your biology teacher may have told you the opposite. If so, they are wrong. Okay, so after you calculate the energy required to break bonds in the reactants, you then calculate the energy that is recovered by making new bonds in the product. So what are the new bonds we've made? We have made 2 carbon double bond oxygen bonds, right? There's only 1 carbon dioxide molecule, but it has 2 double bonds. And how many oxygen hydrogen bonds have we made? 1, 2, but then there are 2 water molecules. So we've made a total of 4 OH bonds. Now there'll be a big table of energies that you will use to add all these together. So here they are. Again, remember I said you broke 4 carbon-hydrogen bonds. Each of the carbon-hydrogen bonds has a bond energy of 413 kilojoules. So simply multiply. You broke the oxygen-oxygen double bond. And since there's a 2, you have to multiply that by 2. The bonds formed, okay, so these have plus values because it's endothermic. They require input of energy. And the new bonds made in the product have negative values, okay, because energy is released. Every single bond that is made is an exothermic process. Otherwise, it wouldn't happen in nature, right? Bond making always releases energy. So once you get all of the signs correct, add them all together, and you will get delta H of reaction. Remember that combustion reactions are always exothermic. There should always be a negative sign. And that's it. So you have learned 3 methods for calculating enthalpy of reaction, as well as a way to directly measure it in the lab with a calorimeter. And that is it for this very long but very important lecture.